welcome to Lesson 5 of Ecological Design Modeling. Today we're going to add to our previous work using the tank model. We're going to explore the ability to adapt it, add some components so that we can model catching the fish that are part of the population represented by the tank storage. So over here, if recall, we have our population of fish, which was our storage. We have an inflow or an immigration of fish that come from outside our fishery. And then we have fish leaving, which are the immigration or the e-migration. So what we're going to look at today is we're going to add a fishing effort. So here we have some boats and some fishermen with nets or lines, some way of catching fish. They have to put in an effort, so they're going to be an extra flow on the extraction of population of fish. And then after they catch those, they could sell those. What we're going to see is that this effort and catch here is going to be represented by our interaction symbol and our process of taking two inputs, multiplying them together to get a product. In this case, we're going to have a fishing effort, population of fish. Those interact, and then we can sell those fish. So we're going to explore the mathematics of what it takes to add fishing effort and the interaction. Let's think about what it takes to catch fish. It takes fishermen and the boats, but how productive is a fishing activity? Well, let's just think about if we have one boat. The number of fish that a boat is going to catch, all else being equal, will be proportional to the number of fish that we have in the population. So if we had no fish, we would have no fish to catch. But as we add more fish to the population, then we're going to see an increase in the number of fish that we can catch. Right? But what if we add more boats to our fishing effort? What's going to happen to our relationship between our number of fish and catch? Well, what we'll see is that we'll catch more fish with more effort, so that for each amount of fish that we had previously with more boats, we're going to catch more fish. So here's if we had one boat. Here, if we had two boats, 3 boats, 4 boats, and so forth. So this interaction will represent this, because if we have more fish or more effort, we'll have more landings, boats, fish to sell. So there's an interaction here between effort and population. And this is the basis of our mathematical expression that we'll have for this pathway. Before getting to modeling our fish example, we need to explore the interaction symbol. This is one of the most important symbols that we'll encounter in the energy system symbol language. It's basically the brains behind what takes place in a simulation model, whereas the tank model was quite dumb in the fact that it basically just took inputs and gave outputs. The interaction symbol really has multiple lines of communication with other parts of the model, taking information, making decisions, or determining flows, and then taking that information, feeding it back to where it received its information. Here we have the interaction symbol. Let's say we have a force A and a force B. These could be sources of our fish and our fishing effort in the example we're going to look at with fish, but it could be much more generic than that. So let's look at it that way first. So if we have two forces interacting together and we assume they have a multiplicative interaction, then we'll have a product that comes from those that's proportional to the two inputs, A and B in this case. And we'll need a constant of proportionality or a rate constant. So in this case we'll use Kp for product. So the product is proportional to A and B. So if we look at the mathematics of the production function here, we can see that if we have more of A, we'll get more product, or if we have more of B, we'll get more product. Vice versa, if we have less of A, we'll get less product, less of B, we'll get less product. That's not all the interaction needs to do. It also needs to tell us about how much we used of A and how much we used of B. So basically it's taking information from the force of A, so you can imagine little bits of information coming into the interaction from both forces. The interaction determines how much it's receiving from these two sources, determines what the product should be, sends that information forward and that product forward as well. But then it also needs to determine how much it used of A. So in that case, it's going to send information back to the storage of A, or the source of A, to tell it how much it used. In this case, the amount of use is going to be proportional to A times B as well. And similarly, we're going to have the amount of use of B proportional to A times B. So we have a KB and a KA. And then we also are generating waste heat, and we can say that the waste is proportional to AB as well. So we'll use a KW. So we really have to think about that this product is quite different than the inputs. This is something that's a transformation of two inputs to make something that we didn't have before, right? So it should have different properties than the two inputs. So some examples besides our fish, this would have been fish and fishing effort. So we had wild fish being caught by our interaction, producing caught fish, right? Fish that are caught. We also could have water, add some salt. Now we have salt water. We could have mice and a cat. Cat catches mice. Now we have a fed cat. Cat that has eaten. Have a textbook and you reading the textbook. Now you're taking this information and becoming more educated, and in the process you used energy. Your metabolism would create energy as waste sitting there reading. Let me emphasize that the mass balance is the fact that the material used from A and the material used from B, our inputs, has to equal the sum of the material that comes out as product plus the material that comes out as waste. Likewise, we need to have energy balance, so that the sum of the energy used from A and B has to equal the energy produced plus the energy wasted. So we should take a moment to contrast the interaction with the tank symbol. As I said, the interaction is smart. It's taking information, transforming it to create new products, sending information back to where it came from so that decisions can be made there as well, or material removed or added. Contrast that with tank. Tank was very simple. It basically took material in, stored it, and then material was taken out, or material was given as an output. So here, the inputs and outputs from tank had to be the same material. If this was fish, you stored fish, fish left. If this was batteries, these are number of batteries, and these are batteries leaving. Whereas in interaction, if this was fish, you could grind up the fish and get fish meal, or squeeze them, process them, and take fish and make fish oil. Two different products.